Hi, folks. This lecture is lecture 18 in our thermochemistry unit, and it's called Make It or Break It. And it's going to talk about ideas of stability and bond energies. But to zoom out for a second, I realized I haven't really oriented us well enough to this unit. If we think about what the class in general, Chemistry 120, is trying to do, I would call the course goal this, that you're trying to learn how to explain the properties of matter, which we did in Unit 1, and the ways in which matter interacts, combines, and changes, which we started to do in Unit 2. Unit 1 was all about understanding properties. So what is stuff made of? Why is it hard? Why does it boil at that temperature, etc. Unit 2 was a lot of kind of imagining reactions in the gas phase and in the aqueous phase and tracking changes with stoichiometry. Unit 3, we're focused on energy considerations, specifically potential energy considerations, which are associated with attractions and repulsions, and kinetic energy considerations, which are associated with motions of molecules or atoms or ions. And if you do a full treatment of thermodynamics, what you are able to do is predict why something changes or not. We're not going to do all of thermodynamics. We're going to focus this unit on thermochemistry, and then when we finish that, we'll be thinking about light energy. But we're still going to gain some ideas that will help us understand why certain things change or why a substance rearranges or not. So this is just a summary. Potential energy is associated with forces. And so we've been talking about attractions, the force of attraction or repulsions between atoms. And we haven't used the terminology so much, but what we've been really talking about is the potential energy that exists between two charges. And when we talked about gases, we introduced ideas of kinetic energy. So I'm just wanting us to know that potential energy and kinetic energy are going to be central to this unit on energy. Now, you don't have these slides. I just found them. So if you want to take some notes on a separate sheet of paper, that might be good. Before we dig into this lecture, I want to differentiate between two types of change, okay? Physical change and chemical change. You might have talked about these in Chemistry 108 or some introductory chemistry class. I'm bringing this up because Lecture 17 was all about heat transfer, okay? Lecture 17 was focused in this realm, physical change. All we were doing was putting something hot in contact with something that was less hot and looking at how heat, or in other words, kinetic energy, was transferred, okay? So heat or kinetic energy is added to or removed from a system. Whenever that happens, we're talking about some kind of physical action on a system. And that could show up as two things. We focused here in Lecture 17. We thought about changes in motions of atoms or molecules and how those changes in motions result in a temperature change. Okay, we talked about three types of motion: rotational, vibrational, translational. We'll get here toward the end of the unit, but the other kind of physical change you could see is something like a phase change, ice melting or water boiling. When these physical phase changes happen, you're changing how molecules are arranged and you're changing their intermolecular forces. So ultimately, you're changing their potential energy. So I just wanted to note, increasing the temperature of something or causing a substance to change phase, these are physical changes and we can think about them as some kind of action on a system. Today's lecture, though, is going to focus on chemical change, and not just today's lecture, but really the rest of the thermochem unit is going to focus here. Not action on a system, but changes within a system. And our system is usually a chemical reaction, so we're thinking about bond breaking and bond making, Okay, you know that bonds are held together by attractions, and so anytime you're breaking or making bond, you're causing changes in potential energy. Okay, so you might notice changes in motions of atoms and molecules occur because of changes in potential energy that lead to changes in heat and ultimately a temperature change. Okay, so for example, a match burning, there's a chemical reaction happening that is releasing heat. That heat is getting exchanged with the surroundings and causing an increase in motions of atoms and molecules. But ultimately, the change in heat is a result of bond breaking and bond making. So just to make this clear, physical changes are what we talked about in lecture 17, right? If you want to predict the heat exchanged when some substance increases temperature, let's say from 25 degrees Celsius to 100 degrees Celsius, all you need to know is, well, what is the heat capacity of that substance, which you could look up in tables or will be given to you in the problems that we solve. You would need to think about its heat capacity, its mass, and what is the temperature change if you wanted to know the total heat exchanged between the system and the surrounding. And we've talked about heat is spontaneously exchanged from hot to cold. So in this case, the system, if I'm going in this direction, the system is at 100 degrees. And when it cools down to 25 degrees, heat is being transferred out of that system into the surroundings. Whereas if I'm heating or increasing the temperature of a gas, let's say, that heat is getting exchanged from the surroundings into the system, causing the system to be at a higher temperature. Today's lecture is going to focus on chemical changes and predicting the heat exchanged during chemical changes. And the thing to remember is that chemical changes are a result of rearranging atoms, or in other words, changing bonding. So this is an example of hydrogen and oxygen gas existing in a balloon. And if you added a little bit of heat, enough to make this reaction go, you would produce water, and it would cause an explosion. You would see an extreme amount of heat coming out of the system and into the surroundings. So this is where we're going to focus today. We're going to be thinking about how much heat is exchanged when bond breaking and bond making occurs. And before we get there, I just want to define two sets of terms: endothermic and exothermic. So again, for physical changes, something like ice melting or water freezing, endothermic processes are those in which heat is going into the system. Okay, so if the system is my ice cube, okay, why does an ice cube feel cold to your hand? Well, it's because your hand is part of the surroundings and heat is flowing from your hand into the ice, causing it to melt. That's an example of an endothermic change. That's a physical change. A cold pack is an example of a chemical change that's endothermic. There's actually a chemical reaction happening in the bag, and heat is flowing from your hand, let's say, into the bag. That's why it feels cold. Heat is being transferred into the system. Burning a match, however, your hand, if it was next to the match, would feel an increase in temperature. So this is an example of an exothermic process, an exothermic reaction, in which heat is transferred out of the system into the surroundings, and your hand is part of the surroundings. So exothermic and endothermic are terms that we're going to work with today. So before we go on, I just thought I would get our summary sheet and just say, actually, we're probably not ready for this just yet. We'll come back to this at the very end. now we've gotten to the lecture notes that are posted on Canvas. So today we're going to be talking about this concept of stability and how it relates to bond energies. So ultimately we'll be thinking about the energy exchange when you make or break bonds. So we've just kind of talked about this, but I wanted to start by thinking about, let's say, a hot pack. In this case, heat can be exchanged with the surroundings, let's say your hand and the air, when a system being the reaction inside the hot pack, undergoes a chemical change. Okay, so a hot pack involves calcium chloride, and it's a solid inside the hot pack, and there's water often inside the hot pack. And the calcium chloride, similar to the airbags lab, is separated from the liquid water, but when you crunch these things, you end up breaking the seal and allowing the calcium chloride and the water to mix. So it's no chemical reaction, really. It's just calcium chloride is mixing and forming aqueous calcium chloride. And this pack starts to increase in temperature. So heat is getting exchanged. Heat is flowing out of the system into the surroundings. Okay, so this is an exothermic process. And what I want you to notice is that even though it's a physical change that's happening, notice changes in bonding. Okay, think to yourself really quick, solid calcium chloride. What kind of bonds hold calcium 2+ and chloride minus together? This is ion-ion attractions. And what holds water molecules together? Okay, hydrogen bonding is the dominant. So both calcium chloride solid and liquid water count as state 1 of the system. This system, calcium chloride and water, rearrange when the seal is broken, and they rearrange to form aqueous calcium chloride. So actually I'm not going to include the heat because that's not really part of the system. Now think through what kind of interactions exist in aqueous calcium chloride. And this is ion dipole attractions. So notice the changes in bonding. I'm pointing that out because the big idea here is that changes in bonding are associated with changes in heat. So changes in bonding, or you could think changes in attractions, are associated with changes in heat or heat transfer. Okay, so that's kind of an overview. I want to define some terms before we move on. Okay, so because potential energy is related to attractions, anytime you have bond breaking and bond making during a chemical reaction, there's going to be a change in potential energy of the system. Now, what do we mean by system? System is as you define it. It can be any part of the universe that you want to explore. Any part of the universe you want to explore. Okay, in this case, it was the reaction between calcium chloride, not reaction, but the process of mixing, and H2O. The surroundings is everything else. Okay, so in our hot pack example, your hand that touches the hot pack, the plastic on it, the air, anything that's in contact. Now, I kind of mentioned it up here, but when we talk about a state of a system, we're just talking about the way in which atoms are arranged. Or molecules. The way in which atoms and molecules are arranged. So notice calcium chloride and these ionic attractions as a solid, water, hydrogen bonding, versus the calcium 2+ ion being surrounded by water and the chloride minus ion being surrounded by water. The atoms in the system are the same, but the way in which they're arranged are different. And this concept, this is a big idea, stability. We've kind of mentioned it when we've talked about resonance structures. But stability is all about whether or not a system rearranges to another state. A system is stable if it does not rearrange to another state. Now, we did talk about the concept of stability when we discussed acid strength, right? We said you could have some acid, HA, and depending on the stability of the conjugate base, an acid will be strong or weak. So if this acid is less stable than the conjugate base, then the system, HA, the acidic form, will rearrange, dissociate a proton or an H+, and form the conjugate base if this is more stable. Okay, so this is not a new idea. We've been using this concept of stability, but now we have a formal definition for it. A system is stable if it doesn't rearrange to another state. So I want you to use your intuition for a moment, and I want you to think about 5 different examples, 5 different systems. Compare state 1 of the system to state 2 of the system. I would like you to circle whether or not you think state 1 or state 2 is more stable. And I would like you to think about, is the process of change exothermic or endothermic? And how might potential energy be changing? So take a moment, maybe pause the video, and just think through which state is more stable, 2 separated oxygen atoms or an oxygen molecule where the 2 atoms are bonded together. What's more stable, gaseous water or liquid water? you took a moment to do that. I'm going to go ahead and circle the states that are more stable. So two atoms, when they're totally separated, there's less attraction here. There's more attraction when those two atoms are together and bonded. So two oxygen atoms will rearrange to form an oxygen molecule. That's why elemental oxygen exists as a molecule as opposed to two oxygen atoms. Okay, think through neon atoms attracted versus separated. When you put two things that are attracted together, they're going to be more stable than two things that are separated. Think about magnets. When you put two magnets together, they're going to stick. This is the more stable state. This one might be a little trickier, but think about, you have to put energy into liquid water if you want it to turn into the gas phase. But at 25 degrees Celsius, water exists as a liquid. This is the most stable state between the two. Now, if you're talking about water at negative 18 degrees, okay, take water, it's at negative 18 degrees. What state is it preferring to be in at negative 18 degrees? Now it turns out the ice cube is more stable than the liquid water if you're talking about negative 18 degrees. Each of these processes, so starting with state 2 in this case, going to state 1, each of these processes, and then in this case 1 to 2, are exothermic. I'm putting quotes to say they're all exothermic, meaning when you go from two separated oxygen atoms to a molecule, energy is coming out of the system and into the surroundings. This might be a little bit explosive, actually. And in each of these cases, if you think about potential energy as being associated with attractions, in each case we're producing something which has more attractions. And that's associated with a decrease in potential energy. And we'll talk on the next page about why. So if you've taken physics, you might have some experience thinking about potential energy. So I'm going to start with what you might know. I've said before, potential energy is associated with forces. So it's basically a force applied over a distance. In gravitational potential energy, we're talking about the gravitational force. Applied over a distance. So the gravitational force is mass times acceleration due to gravity applied over a certain distance, which is the height. When you're talking about potential energy related to forces of attraction, we call that Coulombic potential energy. Right? It's Coulomb's law, because the force that we're talking about is the force of attraction or the repulsion. Okay, so potential energy is associated with forces applied over a distance. So remember, if we're just talking about force of attraction, then you have Q1 times Q2 over R squared. But when you talk about this force being applied over a certain distance, the distance between two particles, then R's cancel. So you're left with potential energy of attraction just being some constant times charge 1 times charge 2 divided by the distance between those charges. Now, I want to talk about the scale for a second. When we've discussed kinetic energy, the energy that is a result of motion, moving particles, we've said 1/2 mass times velocity squared. So kinetic energy has an absolute zero. Right? Kinetic energy is equal to zero when what? When the speeds of the molecules equal zero. Potential energy, though, has no absolute zero. So for potential energy, the zero is not fixed. It's relative. What do I mean by that? If you were to talk about gravitational potential energy, usually the potential energy at zero is associated with the ground. So this cup that's resting on the ground, it has no height above the ground, so its potential energy is zero. This is a low potential energy state. If you were to raise the glass higher and higher above the ground, this distance here is h, the height above the ground. Now, higher and higher potential energy. And think about it, you'd have to put energy in to raise the glass. And when the glass falls, the kinetic energy that it has, the potential energy is getting transferred out of the glass, out of the system, and it's getting converted to kinetic energy until the potential energy goes to zero. With Coulombic potential energy, remember that attraction is between a negative and a positive charge, and the distance between them is always a positive number. So the potential energy of attraction is negative. So as Q1 and Q2 get bigger and bigger, as you have more and more potential energy, more and more attraction, that's associated with negative potential energy. So for Coulomb's law, the potential energy of zero is associated with charged species completely separated, okay? Or the way to think about this might be when R is infinity, when, oops, oh, I didn't realize you couldn't see all that, sorry. When the distance between Q1 and Q2 is infinity, if you divide a number by infinity, you're basically getting closer and closer to zero. So when R is infinity, you're talking about completely separated charges. And you're talking about no attraction. Right? If two things are totally separated, that's when potential energy is zero. This is by convention. Some chemists decided that this is what we were going to call potential energy zero. And then as those particles get closer and closer together, right? Let's think about these two ions. As they get closer and closer together, more and more attraction, the potential energy is a bigger negative number. Okay, so a bigger negative number is associated with low potential energy. And the low potential energy state is associated with being more stable. So having two charged particles completely separated from each other is less stable, right? Because we said that the most stable state is the state that atoms or ions rearrange to. So when you find sodium chloride in nature, it's always bonded in an ionic substance, right? You would have to put energy in to separating this because there's a force of attraction holding them together. So anytime you put energy in, you'd be raising their potential energy. So less stable states are associated with high potential energy. That's true over here too. The low potential energy state, this is more stable to have that cup resting on the ground than to have it in the air. How do you know? Because if you drop it, if you stop holding it above, this state rearranges to this state, the more stable state. Okay, so the last thing I want to have you guys can write down is that strong attraction is associated with negative potential energy values, which we talk about as lower potential energy. So the bigger the negative, the lower the potential energy, the stronger the attraction, the more stable. Those are connections that you need to be able to make. Okay, this was in the case of an ionic bond. Let's think about covalent bonds. So if you're with anyone as you're watching this, feel free to actually participate in the turn and talk. What I want you to see is that this is an energy diagram. Okay, the scale of the graph is potential energy in kilojoules per mole. The x-axis, notice, is distance r. So this is where two charged particles are, there's no distance, they're totally overlapping. And way out here is where the distance of r is infinity, okay? So potential energy is 0 for infinite separation. Kind of have just defined that. I would pause the video right now, and I would do this. The energy diagram below depicts changes in potential energy of two oxygen atoms. So here's one oxygen atom, here's a second oxygen atom, and they're starting at potential energy of 0, which means that R equals infinity. These are completely separated. Construct an explanation for why the potential energy of these two oxygen atoms first decreases on the graph, right? We're getting to lower and lower potential energies, and then sharply increases. See if you can come up with an argument to explain that. And then I want you to think about how would this graph change for a stronger bond? So go ahead and pause the video, think through those two questions. Okay, welcome back. Hopefully you did that. I'm just going to remind us here, potential energy of attraction is some constant times Q1 times Q2 over R. And when R is infinity, the potential energy is 0. Okay, so these two atoms right here are infinitely attracted. But as they start to come closer and closer together, meaning as their distance gets closer and closer, they start to feel attraction. So think about, what is the atom made of? Protons and electrons are the charged particles. So two oxygen atoms are going to start to feel some attraction between their valence electrons and the nucleus. Okay, that makes sense. Now, when are they feeling max attraction? They're going to keep coming closer and closer together until they reach a place of maximum attraction, right here. This is the lowest potential energy. And the maximum attraction is actually what defines the bond length. So if you were to take the lowest part of this curve, okay, and trace it up to figure out what is the radius at that point, I think the radius here is given in angstroms. This radius right here would define the bond length of the covalent bond. Okay, now think about what happens. What if you go beyond this point of maximum attraction? There's a certain place or a certain distance at which the nuclei in both of these atoms, right, the two positive nuclei, start to get close enough that they repel each other. And repulsion would mean, Q1 is positive, that's one nuclei, Q2 is positive, that's another nuclei. Their distance is positive, so the potential energy of repulsion is positive. So notice less and less attraction until we actually get to force of repulsion being the thing that's acting here. So when repulsion occurs, between the two positively charged nuclei, those nuclei are too close. That's why you get this sharp increase in potential energy. So high potential energy, this is a state that's not so stable. Down here, very stable. And the last thing I wanted to point out about this graph is that if you take the difference between potential energy of 0 when they're totally separated and the potential energy when they have max attraction, I'm going to just see what is that potential energy. It's like around negative 500 kilojoules per mole. This distance here between the two is what we call the bond energy. So right now I'm just going to label it as delta H, which we'll learn what that means soon, is the bond energy. Okay, so take a moment to think about this. Bond making, is that an endothermic process? Is energy going into the system? Or is it an exothermic process? Is energy coming out of the system? And if you need some help, look up here. Bond making is you're going down, right? You're forming an ionic bond. Energy's coming out. You're starting at high potential energy and going to low potential energy. So energy is coming out of the system. So anytime you make a bond, it is always, always, always exothermic, right? I'm just going to put it here. This right here, exothermic, potential energy is decreasing, so energy is coming out. If you ever want to break this bond, think about this bond where there's tons of attraction, you want to separate it, you got to put energy in. So if you want to break a bond, so this is bond making. If you want to do some bond breaking, you're going to have to put energy in. Always, always, always. If you want to break a bond, it's an endothermic process. So the question then we want to explore is, well, cause the bond energy to increase or decrease for a particular set of bonded atoms? And again, my computer has shut its screen, so I need to turn it back on. Okay, so I can now see this. All right, so we know that bond making releases energy, bond breaking takes energy. Notice that these bond energies are all positive. Okay, so think for a second. Is this the energy to break the bond, or is it the energy to make the bond, given that the bond energies are positive? I'm just going to go back really quick. If the bond energy is positive, it's because you're putting energy in. Okay, so all of these bond energies are written in this direction. The bond energy is measured by taking the bonded pair and figuring out how much energy do you have to put in to separate the bonded pair. So bond energies are always positive because you're talking about two oxygen atoms that are bonded. That's state 1. And you're asking how much energy does it take to separate two oxygen atoms, state 2. So when you see these values, right, knowing how much energy it would take to separate two atoms can give you a sense of how strong the atoms are bonded together. So we're kind of asking, why is it that some bonds are stronger than others? So I want you to examine the table of bond energies and record at least 3 variables that you see that account for the trends in bond energy. When you find that variable, I would like you to record it here, and then I'd like you to write a claim about how each variable affects the bond energy. So if this variable matters, why? What is your claim? And make sure you provide evidence by listing at least 3 pairs of bonded atoms to support each claim. And knowing that the bond energy is related to Coulomb's law, related to attractions, consider how Coulomb's law will help you account for trends that you notice. So pause the video and see if you can find 3 variables that affect trends in bond energy. Okay, welcome back. So the first thing that you might have noticed is that bond order matters. Okay, I'm controlling for variables here. I'm looking only at carbons bonded to each other. Bond order here is 1, 2, 3. So I'm looking at the number of bonds. So what is the trend? Okay, well, as the number of bonds increase between two atoms, what's happening to the bond energy? It's increasing pretty drastically. So the bond energy increases. Our evidence is that if you look at carbon-carbon, carbon double bonded, carbon triple bonded. Then the bond energy is 347 kilojoules per mole, 611 kilojoules per mole, and 837 kilojoules per mole. So what's the Coulomb's law argument? Well, when there's more bonds holding atoms together, more attraction. So as bond order increases, we can also say, look what's happening to the bond length. It's decreasing. Bond length decreases, more attraction, holding those carbon atoms together. So it's going to take more energy to break this bond. More energy to separate these carbons in the triple bond. All right, you might have also looked at polarity as a variable. You could have compared C double bond N, C double bond O, C double bond C. So you're controlling for the first atom, they're all carbons. They're all double bonds, so you're controlling for bond order. And it's true that the radii is decreasing as you go to the right on the periodic table. So oxygen's a little bit smaller than nitrogen, a little bit smaller than carbon. But the bigger difference is going to be in electronegativity. That's the main effect since they're in the same row. So this bond is most polar, most electronegative, and you can see 799 kilojoules to separate 1 mole of bonded carbon-oxygen atoms. Decreases, it's a little easier to separate carbon and nitrogen, and it's easiest to separate carbon-carbon. So as you increase bond polarity, you're increasing attractions. The more electronegative atom can kind of have more of a partial, I'll put it here. There's a bigger partial negative, a bigger partial positive here, and that creates kind of an electrostatic attraction. You have this negative attracting this positive. And that's going to mean increased bond energy. So this was looking at this trend in electronegativities. You could have also looked at HC, HO, HF, and you would see the same trend. So H is controlled for more electronegative going down, and you see the bond energy increases. So HC, HO, HF, 414 kilojoules, 464 kilojoules to separate oxygen and hydrogen atoms, and 565 kilojoules to separate a fluorine and an H atom bonded. Okay, finally, zoom out a little. Oh, sorry, I didn't realize you couldn't see that. Let's see if we can see the whole sheet. Good enough. All right, we'll live with it. Okay, the last thing that I want to point out is bond length. Or really, we're talking about atom size. So now I would point you to compare HF. Cl is right below F on the periodic table, and then Br. So these three for atoms size. So smaller the atom, notice, larger the bond energy. So as bond length decreases, as those atoms get closer together, the amount of energy you have to put in to separate them increases. So as the sizes of atoms get smaller, the bond length decreases and the bond energy increases. And we saw HF, HCl, HBr, 565 kilojoules to separate those two, only 431 to separate H and Cl, and then only 364 kilojoules to separate H and Br. Notice that's a really big difference. Size has a bigger effect than electronegativity did. But still the biggest effect is bond length. Sorry, bond order. Okay, so I just want to point us here to let you know that these bond energies can be used to help us make predictions about whether reactions will be endothermic or exothermic. Whether reactions will be endo or exothermic. And we'll be talking more about that in the next lecture. Okay, so I want us to think overall. We've talked about changes in potential energy, but energy overall has to be conserved in a chemical reaction. So we better start thinking about if potential energy is decreasing, what's then happening to kinetic energy? So going back to the two oxygen atoms, really quick, let's look. O2 has a bond energy of 494, which means if you want to start with an oxygen molecule and you want to separate that bond, you want to go up, you want to put energy in to separate that bond, you have to put in 494 kilojoules of energy if you were going to separate a mole of oxygen molecules. Just to kind of point that out. So let's go back here. Now we're starting with two oxygens separate, and we're going to look at forming the molecule. So this is my state 1. Okay, the oxygen atoms, two oxygen atoms are arranged to be very separate from each other. State 2 is in the molecule. So two bonded oxygen atoms. Okay, what is the potential energy of two fully separated oxygen atoms? Should be 0, right? There's no attraction here. So on an energy diagram, I'm going to erase this just so you can kind of see it a little bit more clearly. Notice that this is state 1, with a potential energy of 0, 2 separated oxygen atoms. But we know that these oxygen atoms must have some kinetic energy that's positive, right? Because the atoms are moving. And they have mass. So that's state 1. Potential energy is all that's represented on this energy diagram, but we're just saying we know that there is some kinetic energy that these atoms have. Now, when the reaction occurs, when the oxygen atoms bond, what happens to potential energy? It gets more negative. The language you use to say it gets more negative is that the potential energy decreases. Okay, if the potential energy decreases by 494 kilojoules per mole, right? Then what happens to the kinetic energy? It must mean that these oxygen atoms are moving faster. Look at the vector. This is a longer vector than this. This is supposed to show, slowish and then faster oxygen atoms. So when potential energy decreases like this, it must mean that the kinetic energy of these molecules increase by the same amount. So kinetic energy is getting more positive. So you can think through, right? Increasing, if these are molecules, they're going to increase their vibrational motion, their rotational motion, and their translational. So they're going to be hotter, a higher temperature. So whatever the temperature of these oxygen atoms were when they were separate, right, they had some temperature, they got hotter. You could think of it as hot products getting made. Now go back to lecture 17. If you have these hot oxygen molecules in contact with the rest of the air, or I'm just going to say in contact with surroundings, okay, now you're going to have heat transfer. So then the O2 molecules transfer heat to surroundings. Okay, what do we call that process when heat is transferred out or energy is going out to the surroundings? Right? We call that exothermic. So this is again just showing us that making bonds is exothermic, releases energy to surroundings. Okay, and so the reason that let's say if this were to happen, you might see a little bit of an explosion. What's going to happen is that you lower the potential energy of oxygen, it increases its kinetic energy by the same amount. So I should put increased kinetic energy up here. And then all that kinetic energy is going to get transferred out of the system, out of this system, and into the surroundings. So I'm going to just add plus heat. And where is that heat going? To the surroundings. Okay. So we're going to think it through another set of terms. Enthalpy is a term that we're going to be using for the rest of the unit. It is synonymous with heat of reaction, and abbreviated delta H. And my computer again. Okay. So I just want to go through a few points before we define it. Anytime you have potential energy differences between reactants and products, that energy difference, right? Any energy difference between reactants and products, that energy difference is going to be transferred in the form of heat. And heat we abbreviate as Q. In other words, okay, chemical reactions are either going to release or absorb energy by changing the temperature of their surroundings. When you transfer heat out, you're changing the temperature of the surroundings. So anytime you have a change in heat, anytime heat's being transferred, that's going to be associated with changes in bonding. Okay, so the change in enthalpy, this delta H is what we'll start referring to it as, is defined as the change in heat between two different states of an ensemble of molecules at a constant pressure. All that means, right, that enthalpy is the change in heat between two different states. So from state 1 to state 2, this change right here, represented by the black arrow, is the enthalpy. So the heat of reaction, or the enthalpy of the reaction, is really just how much heat is exchanged during a chemical reaction. How much heat or thermal energy is exchanged during a chemical reaction. And all of that amount of heat is going to be associated with the strength of the bonds that you're breaking in that reaction, and the strength of the bonds that you're making. Because the strength of bonds is related to their potential energies. So a few terms here. An endothermic reaction is associated with a positive heat of reaction. Okay, that means the positive, I don't want you to think that's negative. I just want to emphasize this positive is showing that heat is absorbed. By the system. So a potential energy diagram, which we're going to be using these a lot, just models potential energy between state 1 and state 2. State 1 has a low potential energy, and heat is getting absorbed, so delta H is positive to get to state 2. That's what an energy diagram would look like for, I see you can't fully see this, for an endothermic reaction. An exothermic reaction, the delta H, or the change in enthalpy, is negative. Heat is transferred out. Out of the system. So your potential energy diagram looks like state 1 being less stable and you're making something more stable. You're decreasing the potential energy. The change in enthalpy, or the heat of the reaction, is negative. And delta H is associated with Q. You might be asking, if we're talking about delta H as heat of reaction, why are we not just saying Q like we did in lecture 17? Q is associated with the change in heat, except for the fact that Q is a total heat that's exchanged. And delta H is associated with the stoichiometry of a reaction equation. What do I mean by that? Oh, and it's often measured in kilojoules per mole. What do I mean that delta H, or the heat of reaction, is associated with the stoichiometry of the reaction? What I mean is that like the delta H of this reaction, two oxygen atoms forming a bond, we already saw that the bond energy of separating two oxygen atoms is plus 494. If I'm talking about making the bond, then I have to say negative 494. That means if I have 2 moles of oxygen atoms coming together to make 1 mole of oxygen molecules, if I have that exact amount, then I'm going to be releasing 494 kilojoules to the surroundings. So if this had different stoichiometry, different numbers of moles, then, well, I don't want to explain it like that. All I want to say right now is that this 494 is associated with there being 2 moles of bonded atoms coming together to make 1 mole of oxygen. And so anytime you have a reaction equation written, you can write a delta H that's associated with it. If I increase my number of moles, let's say that I actually have 4 moles represented in here, then I would times this by 2. So this is for 2 moles of O2 making, 2 moles of O making 1 mole of O2. Let's say there's 1, 2, 3, 4, 5, 6, 7. Let's just say that there's 8 moles of oxygen atoms, meaning I'm going to make 4 moles of O2. I'd have to multiply this number by 4 if I wanted to know how many kilojoules of energy would be released if I made 4 moles, because this number is only associated with the reaction equation. That will make more sense as we see delta H's used in context. All right, the very last thing I want to talk about, or I just kind of want to pull this all together. So let's say that you had a hot pack reaction. You had calcium chloride solid and you added it to water and you made aqueous calcium chloride. This is your system, okay? 1 calcium ion, 2 chloride atoms, 2 hydrogen atoms, and an oxygen atom is your system. They rearrange to form aqueous calcium chloride, right? Ca2 plus is now being surrounded by water molecules on all sides. It's being solvated. Okay. I want you to think about endo or exothermic, positive or negative delta H. How would you represent state 1 and state 2 of the system on this energy diagram, how would you explain, we're going to call it the enthalpy of dissolution, because it's not a reaction, it's just calcium chloride dissolving. How would you explain the sign of the delta H in terms of bonding and attractions? Write yourself an explanation. And then how can the first law of thermodynamics explain why the solution gets hot? Please pause the video, try this. This is like an exam type question. Okay, welcome back. Notice if the calcium chloride, once it dissolves, feels hot to your hand, what does that mean? It means that energy is coming out of the system into the surroundings. So that must mean we have an exothermic process with a negative delta H. So if I wanted to represent state 1 and 2, and it's exothermic, I know that state 2 is more stable. It has a lower potential energy than state 1. So that explains the sign of the delta 8. Energy is coming out. So how do we explain the negative delta H in terms of bonding or attractions? Collectively, there must be, this is more stable. So there collectively must be more attractions or stronger attractions. In this arrangement. So I could say, what kind of attractions exist here? Here. Ion dipole. So I would say the ion dipole attractions between water and the Ca2 plus cation and the Cl minus cation, not cation, anion, are collectively stronger than the hydrogen bonding and ion interactions in state 1, which is CaCl2 solid and H2O liquid. That might seem counterintuitive, but you can fit somewhere between 4 and 8 waters around each calcium 2 plus, and similar for each chloride. So if you add up all of these ion dipole interactions, they're actually going to be collectively stronger than having the ion-ion or the hydrogen bonding interactions. That's why you have a negative delta H. That's what a negative delta H means. You're making stronger bonds, or in this case IMFs, in the products. Oops. This is the way to interpret what a negative delta H is. You made some product that's more stable, that has stronger interactions or attractions than the reactant. Now, what about this second part? How can the first law of thermodynamics explain why the solution gets hot? Okay? That's basically going back here to conservation of energy. So here we said Changes in potential energy lead to changes in kinetic energy. So let's think about it in this case. What's happening to the potential energy of the system? It's decreasing. So overall, the potential energy of the system decreases. And that means the kinetic energy of the system increases. So if I knew exactly what value this was, the exact amount of increase would happen for kinetic energy. So what do I mean by that? These calcium chloride ions moving around with the water get hot. Okay? And then what's going on is their temperature of the solution has increased, gotten hotter, and now heat transfer is occurring between the hot solution and your hand, or the hot solution and the air. So overall, the potential energy, I'm going to just do this so you can see it, potential energy of the system decreases. That means the kinetic energy of state 2 is now high. And because the calcium chloride is in contact with the surroundings, overall heat is going to be transferred out. Heat is going to be released to the surroundings. So to just finish this explanation, the kinetic energy of the system increases because CaCl2, because aqueous calcium chloride is in contact with the surroundings, the system transfers heat to the surrounding, resulting in a temperature change. Okay, that is the end of this lecture. So just to review, you should be able to describe energy exchange that occurs in making and breaking bonds. You should be able to explain the variables that affect bond strengths and therefore bond energies. Not listed here, but you should be able to apply the first law of thermodynamics, or conservation of energy, to an exothermic or an endothermic process. And you should be able to represent changes in the system on a potential energy diagram. And I said we'd come back at the end to that summary sheet, which is here. Okay, so we can add some things to it. Maybe you want to try and add them before me so you can check yourself. Exothermic, delta H is negative. The potential energy of the system is decreasing, getting more negative. That means that the kinetic energy of the system increases and ultimately heat transfers out to the surroundings. Overall, the attractions within the system, if the potential energy is decreasing, then the system is having stronger attractions. And the potential energy diagram looks like this. If If you have an endothermic process, delta H is positive. The potential energy of the system is increasing. Heat is transferred in. So the system, if we do it like this, the system is getting less stable. So heat is transferred into the system. You could have thought of this as out of the system to the surroundings. This is into the system from the surroundings. The overall attraction within the system, less attraction. Or maybe weaker, just to be parallel with this. We'll see more problems like this, but I did say that the enthalpy is associated with the stoichiometry of the reaction, and we're going to see that if you wanted to calculate the heat transferred by a chemical reaction, you'd be thinking about how many moles reacted or got produced times the delta H of the reaction. And I've barely introduced this, so we'll come back to this. Next lecture, we're going to be talking about how do you calculate the heat of a reaction using bond energies. And then we'll be contrasting that with how do you calculate the heat of a reaction using heats of formation. And then we'll end this thermochemistry series by looking at heat transfer that results in a phase change. All of them have different Q equations. So I will post this lecture on the home page under Lecture 18 Bond Energies, and you can find the printout of the notes there as well. And I will see you back here for Lecture 19.